Hi everyone. This time we're going to have a look at some typical mechanics, or more precisely, statics questions you will encounter in exams. So they all either you end up with a bunch of forces that you need to decompose and find some unknown forces, or you may end up with questions in terms of movements and reactions and all that. So I'm just going to go through them, and like so you get a quick you get some idea about how to approach these things. So firstly, the scenario is you have a load here, the crane is pulling one way, this dude is pulling the other way. Yep. And then if the whole thing remains static, it will be in equilibrium, which means all the forces will cancel out. Yeah. And what we can do is firstly we'll do a free body diagram to simplify the force system so we know which forces are actually acting on it. So obviously we start with A. There is the crate going down with a force of 5,000 newtons. Yep, because 500 kilo we take N approximately equal to 10. And then another force, the dude pulling, which should be, let's just call it tension, because tension is what we are looking for. And of course, there is the cable from the crane, yeah, which is let's just call it P because it's pulling. Okay, now the angles, obviously, P is 10 degrees from the vertical, so it should be 80 degrees from horizontal, while T is, actually, let me do a shorter line. T is 35 degrees. Yep. Okay, so these are the three forces acting on it. The cable of the crane pulling, some guy pulling the rope, and the weight going down. Now we need to find the tension in the rope. So the tension, we need to find what T is. So that means we need to figure out the how the forces are arranged in this system. So the easiest way to do it is to do a force decomposition. Yeah, so break P and T into their vertical and horizontal components. So P equals to, yeah, this is the vertical component. Yeah, would be too squiggly, and this is the horizontal component. Of course, T. Sorry. So T is also has a horizontal component and a vertical component. Obviously, it's not really to scale because these two probably should be the same because they're the only two horizontal forces. Of course, what we can do now is we can label them. The horizontal part of P is 80 degrees here, so this should be the adjacent side. So it should be P cosine 80. Well, the other one is P sine 80. Similarly, for tension, this will be T sine 35, and this will be T cosine 35. Yep. So these are the forces. Now, if the whole thing is in equilibrium in the horizontal direction, so it means that the system doesn't go left, start moving left and right, then these two forces have to cancel out. Yeah. So if all the horizontal forces in the x direction has to be 0, then T cosine 35 has to equal to P cosine 80. Yeah. Similarly, if we look at vertical direction, the vertical direction, you can see P sine 80 is going up. The two forces counteracting it will be this one, T35, but also the weight of the crate. So we would end up with this, T sine 35 plus 5,000. Yeah. So that's our two equations. Here we show that the horizontal parts of t and p has to equal to keep it stationary, keep the system stationary in the horizontal direction. And then the vertical part of p has to equal to the tension dragging down and the weight dragging down as well. Yeah. So that's our pair of equations. So levels 1 and 2. Okay, now what we need to do is to solve them for t and p. But as you can see, we have two simultaneous equations. Yeah, so two unknowns, two equations. That's simultaneous equations. So here, substitution is probably easier because if we can replace the p here with something in terms of t, then we can have the whole expression expressed in terms of t, and one variable, one unknown, one equation. It's just solving a very basic equation. Yep. So now, what does p equal to? We can see that t cosine 35, because we need to divide both sides by cosine 80. Yeah, so what do we end up with? So t cosine 35 over cosine 80 equals to p. Of course, we can just replace this p with this one. So t cosine 35 over cosine 80 equals to t. Sorry, I forgot that. Oh yes, that's right. So t. Sorry. Left the sine 80 part out. Sine 80 equals to t sine 35 plus 5,000. As you can see here, we have sine 80 and cosine 80, isn't it? So sine divided by cosine is tangent. So we end up with t cosine 35 times tangent 80, which equals to t sine 35 plus 500. Then we can just move all the t's to one side, and so we end up with t cosine 35 tan 80 minus t sine 35. Sorry, again. It should be 5,000 equals to 5,000. Now, what we have here is a single equation, and we can factor t out. Of course, if you really want, you could have just got numerical approximations for these trig values. But I tend to keep them until the end to make my answer slightly more accurate. So, of course, we can factorize the t's out, and we end up with t cosine 35 tan 80 minus sine 35 equals to 5,000. Yeah, and of course we can divide both sides by everything inside the parentheses, so we can end up writing as t equals to 5,000 divided by cosine 35 tan 80 minus sine 35. Yeah, so that's our answer. And if you punch all of these values in the calculator, you will see that t is approximately 1,227.9 newtons. So that's very straightforward. Only thing you need to worry. The main thing is do the free body diagram and find the force components. And if you're two unknowns, you do a substitution with the simultaneous equations. Yeah? Okay, now let's look at the other one with things like moments and reactions. Yeah. So obviously we need a free body diagram. Okay, so what does it look like? It will be, obviously we'll have our wheel. It will be pretty crude here. Yeah. I'm trying to make it good. All right, this is as good as can be. Now, of course, we need a distance here to the pin, which is 200, and then the distance between two pins here is 40. So this one screw here and one pin here. And of course, we have two pulleys, the forces 300 newtons here, and then 300 newtons here. Okay, so how do we approach this? Now, if we look at it, we can see that this bolt here fixes everything in place, and the lower pin, it's inside a slot, which means it cannot handle up or down motion. Yeah. So it cannot resist up and down motion, and it cannot resist rotation. So what that means is that you can look at these two forces. What they're trying to do is that these two forces will try to rotate the whole system. In the counterclockwise direction about the pin here. Yeah, so these two forces, as you can imagine, these two forces dragging down and they're trying to rotate the whole thing counterclockwise about this point. And what's stopping it from spinning will be the reaction on this pin, yeah, because the pin is being pushed against the side of the as a slot, as you can see here. So a reaction here, yeah, will produce the moment about 40, which spins the whole structure clockwise, canceling out the this particular moment. So to cancel out the moment generated by the weight drag down here, because you have forces to a distance to the center, so it's trying to spin the whole thing, but a reaction here pushing against the pin stops the thing from spinning. Yeah. So that is the premise of it. An easier way, of course. An easy way to do it is to identify the resultant force of this these two forces, isn't it? Because as you can see, it's a spinning wheel. So the only force the rest of the structure experiences is through the pivot here. So what we can really do is to turn these two, add them together, and make them a resultant force in the middle. Yeah, so this is what we're aiming for, resultant force. Now, if you really want, you can draw the thing to scale and then add them two together. Yeah, and then so this this goes here, and then you find the vector sum. Of course, as you can see, that the quality of the drawing on this presentation, like I won't be able to actually do it, so I have to solve them algebraically. Now, the quickest way to look at this is what are the components of each force? So here, once again, we have two components, yeah? So, of course, this one, the one on the left, only has one single component. But the other one, well, what's the angle? Angle is 30 degrees here. So the angle here should be 30 degrees, which makes this side the opposite side, because it's the same as this one. So these two sides are equal, which means this side should be 300 sine. That's horrible. 30, and of course the vertical one should be 300 cosine 30. So that's what we have. Now, if we want to find the resultant, resultant force will be the sum of all of these. Yeah. So in the vertical direction, we have 300 cosine 30 plus 300. Yep. So this is all the forces in the vertical direction. And in horizontal direction, there's only one because this force goes straight down, so it doesn't have any effect horizontally. So what we have is next one will be 300 sine 30. Of course, I'm sure you can tell where this is heading because if we want to find the resultant force R, crap, it's the same. So resultant force, just let's call it force F. Yeah. Okay. So as you can see here, we have the vertical component, these two together, and horizontal component. So to find F itself, we have to do the Pythagoras theorem. Yeah, we have to. Yep. So of course, this first part is the sum of these two forces going down, and then the horizontal part is just this force. Now, what do we end up with? So F should be approximately 579.56 newtons. Okay, yeah. Now, now we have found our total resultant force. We want to find out what the reaction at the pin here is. Yeah, so what does R equal to? Now, as I mentioned earlier, the force R here is resisting a rotation counterclockwise. Yeah, which means the moment generated by R times 40. So if the sum of all the moments has to equal to 0, then we have to say, what's the downward force though? So downward force is just the sum of these two, aren't they? So there are only two. Well, this force, the 300 times sine 30, because it's acting in the direction, acting towards the pin here, so it doesn't actually generating any moment. The only thing that generates moment are the two vertical components. So what does that mean? It means 300 plus 300 cosine 30. So the two vertical forces here, this is their sum. Yeah. What's the moment they generate? What's the arm of the moment? So times 200. So I just might use meters so I can have the answer in Newton meters. Yep. So it's 0.2. So this is the moment. The total force of the cable pulling on the pulley times the distance of the pulley from the center of the pulley to the pin it's mounted on. So the screw it's mounted on. So for the whole thing to not spin around, then it has to be this whole moment, the force times the distance, has to be cancelled out by, also force times. So it should be 0.02. Yeah. Okay. Now we can just solve this equation for R. So R equals to, divide both sides by 0.02. Sorry, 0.04. Yeah, so we end up with 300 plus 300 cosine 30 times 0.2 over 0.04. Wait. Better. All right, so what we end up with is R should be approximately, if you punch all of this into the calculator, should be about 2,799 newtons. And so there is that.